Hi, thank you for joining us on NASA Television for NASA's Asteroid Update. I'm Public Affairs Officer Trent Parado. We have a lot of exciting news to cover today on NASA's asteroid work. Now, you may know that NASA tracks near-Earth objects like asteroids, and this includes potentially hazardous ones. You may have heard of the Asteroid Grand Challenge, which is where the public can actually help accelerate NASA's work hunting for potentially dangerous asteroids and coming up with ideas on what to do with them. You'll hear much more about NASA's detection efforts in the Asteroid Grand Challenge, which just celebrated its one-year anniversary yesterday, coming up in the program. You'll also hear much more about NASA's Asteroid Redirect Mission. Now, this is an effort to send a robotic spacecraft to an asteroid, capture the entirety of it or maybe a portion of it, move that asteroid mass to a stable orbit around the moon, where astronauts will visit it in the 2020s and return to Earth with samples of that asteroid. In doing the mission, we'll test a number of the key technologies and capabilities we need for future human missions to Mars. So it's a very exciting time here as NASA's on the path to send humans to Mars, and asteroid plays a big part of that. A lot of exciting asteroid news to come. We have a distinguished panel of guests here in Washington and joining us virtually to tell us more about that. I'd like to introduce each of them. They'll give brief remarks. We'll circle back for question and answer with the press. If you're joining us online, you can ask questions of the panelists using the hashtag on Twitter, AskNASA. We'd also encourage you to join the conversation online on Twitter using the hashtag NASAAsteroid. And of course, you can find out more information about everything you hear here today on the web at www.nasa.gov/asteroid initiative. I'll begin by introducing our panelists here in Washington. To my left, I'm joined by Michelle Gates, who is the Program Director for NASA's Asteroid Redirect Mission. With Michelle here in Washington is Lindley Johnson. He is the Program Executive of NASA's Near-Earth Object Program. Headed out to the West Coast to our colleagues at JPL, the Jet Propulsion Laboratory in Pasadena, California, we are joined by Paul Chodas. He's a Program Scientist at NASA's Near-Earth Object Program. Farther west, we go to Hawaii. We're joined there by David Tholen. David is an astronomer at the University of Hawaii. His colleague at the University of Hawaii, research assistant Marco Michelli, is joining us by phone. He's currently in Frascati, Italy, where he's working at the European Space Agency Near-Earth Object Coordination Center. Next, we go to Arizona, where we are going to Northern Arizona University, where we're joined by David Trilling, who is an associate professor, and Michael Momert, who is a postdoctoral researcher. We head back to California at NASA's Ames Research Center at Moffett Field in California, and we're joined by Jason Kessler. Jason is a program executive for NASA's Asteroid Grand Challenge. He's at Ames. He works here at headquarters. He's at Ames right now at the Solar System Exploration Research Virtual Institute, or SERVI. You'll hear more about the two-day workshop that Jason and SERVI are working on right now. The Asteroid Grand Challenge, which I said before, is the public's opportunity to engage with us in the hunt for asteroids. So with that, we'll begin here in Washington with remarks, and we'll start with Michelle Gates. Michelle?
Hi, good afternoon. It's great to be able to share with you just a little status of where we are with the Asteroid Redirect Mission. As you may know, the mission consists of three very important elements, the first being the identification of candidate target asteroids, which our colleagues here will talk more about in this segment. Excuse me, you can see on the slide the ground and space assets that we use for observation, tracking, and characterization of these small bodies. Second is the redirect element, in which we'll launch a robotic spacecraft to redirect a small asteroid to a stable location in lunar orbit. The third element is the exploration element, where our crews will launch on the SLS and Orion spacecraft to explore and take samples of the asteroid and return them home with them. Next. So this is our latest really quick animation with some updates showing the high-powered, long-life, solar electric-powered spacecraft executing one of two of the capture options, and the astronauts launching on Orion, traveling through lunar gravity assist, egressing from Orion, translating hand-over-hand translation in that particular concept, removing samples, practicing all the techniques that we'll need in future in-space EVA, as well as low-gravity body sampling. Next, please. We're actually leveraging several ongoing activities across the agency. You see here 2 advanced solar array systems technology developments, which are both actually wrapping up their current work at vendors through the Glenn Research Center in Ohio. Next slide. Several activities here on the International Space Station, including some robotic, advanced dexterous robotic manipulator activities. There's a refueling demonstration, the International Docking Mechanism. We're also looking at common rendezvous sensor suites and mechanics for boulder extraction. Next slide. Our astronauts and test crews have been busy this year working in the neutral buoyancy lab at JSC, testing out some of our concepts, techniques, and tools for implementing this mission. We've actually spent the last year and will continue to advance the plans for our in-space EVA suit, as well as the primary life support system, translation aids, and techniques that we'll use on orbit. Next slide. Our NASA Extreme Environment Mission Operations activity has 2 mission operations activities planned this summer to investigate for the Human Research Program, human and behavioral health, habitability, and also something we call telementoring, which is the execution of expert tasks by an astronaut virtually. Next slide. We also wanted to announce today the selection of our broad agency announcements. We have plans to award $4.9 million in response to the BAA release that was in March. We received, 108 proposals and have selected 18 for award. There are 4 proposals in capture systems, 2 in rendezvous sensors, 4 in the adaptation of commercially available spacecraft buses, 5 in the potential partnerships of secondary payloads on the robotic spacecraft, and 3 in potential partnerships for the crewed mission and extensibility activities. Coming up this winter and late fall and early winter, we'll actually be receiving our initial inputs from that BAA concept development work, as well as folding in our internal reference concept activities to choose from one of the 2 robotic capture options, which many folks are already aware of, but the first we call option A, which is the extraction and redirection of a single small asteroid from the near-Earth vicinity, and the second is actually the acquisition of a coherent mass, be it a boulder or a loosely connected asteroid from a larger asteroid. In either of these options, we will demonstrate planetary defense deflection basic techniques, and of course continue to benefit from the important and exciting work in the Grand Challenge, as well as the NEO observation program. Thank you.
Thank you very much, Michelle. Now we'll hear from Lindley Johnson. Lindley?
Thanks, Trent. Michelle. NASA's Near-Earth Object Observation Program is a network of observatories and facilities around the world that are trying to find the population of those small objects, asteroids and comets, which come near the Earth. And some of them could pose a potential impact hazard to the Earth in the future. So we are trying to find that population before they find us. The efforts then you're going to get a good sense of worldwide effort that this is with all the locations we're going to talk to today, and telling you about the process that we go through to find, track, and characterize these objects, both for the purpose of determining where they do represent an impact hazard to the Earth, and then in support of missions like the ARM mission, both robotic and human spaceflight missions. Our network currently is finding about 100 near-Earth objects each month. So our pace at finding these objects continues to increase. We've found about 1,000 in 2013. So we're on a pace to improve that discovery rate with finding about 100 a month now. As we find these objects, we examine their orbits, and there's a small subset of them that are in very close Earth-like orbits that are good candidates then for both robotic and human spaceflight missions and for the ARM mission. So as we identify those, we increase our looks at them with other observatories to characterize them, determine size and nature of them, to really determine whether they would make a good candidate or not. And Paul Chodas is going to talk to you about that process that we go through to do that in a little more detail. As we find these objects, several of them we've actually found before the ARM mission was announced. And this one that we're going to talk about today, 2011 MD, is such an object. It was found back in 2011. And so as opportunities come up to further examine those, like we will talk about today with the Spitzer telescope, we do so to better understand their size and characteristics. This is all good practice for us, though, for the occasion when we might find a potentially hazardous impactor, because this allows us to exercise our observatories and techniques that we'd need to do to fully characterize a potential threat. So it all fits together in the overall objectives and mission of the Near-Earth Object Program. So with that, why don't we get on with the detail and hand it off to Paul Chodas.
All right, thank you, Lindley. So let's go to JPL and Paul Chodas. Paul?
Hi, thanks, Trent. I'm going to provide some of the details to elaborate on what Lindley was just talking about, give some progress on our finding of potential targets for the ARM mission, and I'll say a few words on one particular candidate that later speakers will be talking about. My first slide is a slide off of our webpage, actually, which shows the discovery rate of near-Earth objects, the number of known near-Earth objects versus time. And you'll see the year on the bottom there. And along the vertical axis is the number of known objects. If you look at the very right side, we're up at around 11,000 now, which is the current total number of known near-Earth objects. That's the blue curve. The red curve is just for the large objects. Those are the ones that are 1 kilometer and larger, about 0.6 of a mile or larger. Those are the ones that could, if they hit the Earth, could lead to global catastrophe. So that just indicates what Lindley was just saying, that we're finding objects about 100, near-Earth objects about 100 per month. We're finding them at a good rate. In fact, there's a bit of an acceleration. Since 1998, NASA's NEO observations program has led the international effort to discover and characterize these asteroids. You can see how the curves turned rapidly upwards when the NEO program started in 1998. The total number, by the way, of of all NEAs, near-Earth asteroids, the total number would be in the like tens of millions or hundreds of millions if you go down to some of the small sizes that we're talking about. The next slide talks about the observation programs, the asteroid search facilities that NASA is funding. These are wide-field telescopes that search the dark sky every dark night of the month looking for moving objects. They scan essentially the full sky in over a few days in time. The first one, Catalina Sky Survey, is located in Arizona. Pan-STARRS is in Hawaii. The Space Surveillance Telescope is in New Mexico. That's a new observatory that is just coming online and is has a very large aperture and should provide a lot of NEO discoveries. It'll be providing those in test mode. And on the bottom is NEOWISE. NASA recently reactivated NEOWISE, and it is a space-based survey that is finding asteroids. It has the advantage of being in space, avoiding weather, and is searching in the infrared, where asteroids are particularly easy to find. Now, all of these observatories work with the Minor Planet Center in coordination. They send in their measurements of moving objects. And the Minor Planet Center then determines whether we're looking at an old object or whether it's a new object. So I wanted to mention that they are an important part of this. Within a day or two of finding a new object, these we'll know roughly where the orbit is. We'll get a good idea of the orbit, and we'll have a very rough idea of the size of the object. That happens really very quickly. There's a second process, though, and that's the next slide. discovery is not enough. We also have to consider characterization. That is learning about the physical properties of asteroids. And on this slide, you'll see Goldstone and Arecibo on the top. These are two radar facilities that are really important and very capable of establishing things like the shape, the size, the spin rate, and even surface features on near-Earth asteroids. There was one 10 days ago that NEOWISE found, actually, called 2014 HQ-124, which was observed by radar, and we could actually see boulders on the surface of that asteroid. However, radar is only useful when the asteroid is near enough. On the upper right there are the large optical telescopes. They are very useful for tracking the asteroids, getting more orbit information. They're useful for photometry and determining the brightness, and the variations versus time will indicate the rotation rate of these asteroids. On the lower right is NASA's infrared telescope facility. It provides some ground-based infrared measurements of asteroids. That will tell us things like the colors of the asteroid and give us an idea of the spectral class. Finally, on the lower left is the Spitzer Space Telescope, which you'll be hearing a little bit more about that. That's also an infrared telescope. It's not near the Earth as shown in this diagram. It's actually about 100 million miles or more away from the Earth right now. It's orbiting the Sun. We'll hear a little bit later about how it has just recently observed one of the ARM candidates. So how do we put all this information together? The next slide indicates roughly how it all fits together, starting with observations, which are in the light green there. In the upper left, we have the initial detection, the tracking, the photometry. All of this happens very early. We have a rough orbit. We get an absolute magnitude within a few days. We have additional tracking when available, when the asteroid is bright enough. And then there are these other characterization means which give us more information. The desired information is showed in yellow. We want to know, in particular, the rotation rate, the spin rate, the shape, the precise orbit. We want to know the size. And in the bottom right, we want to know the mass of these objects. So the characterization efforts and facilities are used to get us this information. And that's what we'll be talking about a little bit later, and the following speakers will be talking about. This characterization effort, though, it takes a little bit more effort and more work to get that information. So let me move to the next slide and talk about the candidates for ARM. Now, you heard in Michelle's talk how there are two options. We have option A, which is to find and envelop and capture a small asteroid and bring the entire thing back into orbit around the Moon. And that's what I'll talk about first here. The parameters that we're looking at for good candidates for option A are, first of all, that we have a very accessible orbit around the Sun, and that's kind of indicated in the upper left here, where red is the orbit of the Earth and blue is the orbit of the asteroid, and you can see it's very similar. And this makes it very accessible and easy to put into orbit around the Moon. The middle diagram there indicates we need to have a close approach to the Earth in the early 2020s. That's basically the opportunity that will be modified, and we'll move that blue line over so that the asteroid will be captured into orbit around the Moon. And in the lower right rather, we have the final step, the characterization step, where we want to get the detailed information. We want to have the size of the asteroid less than about 10 meters. Now, initially on the day of discovery, we know more or less what its size is within a factor of several. Maybe a factor of 10, actually. But the characterization step, that final step that I talked about, is necessary to establish the size and whether it's less than 10 meters or not. And that will indicate then also the mass, which is another important parameter. So far, there are probably thousands of candidates out there, but they are very hard to detect because they are small. And so far, we have discovered and characterized a few of them. I'll talk about potential candidates, and those are the candidates that satisfied like the first two of those requirements. But that characterization step, if a candidate asteroid satisfies that, then we call it a valid candidate. So I'll be using those two terms, potential and valid. The next slide is for the other option, option B, where we will go to a larger asteroid, one that's maybe 100 to 500 meters. The size is not quite so important. And its orbit it doesn't have to be quite so accessible. I'm showing the orbit of Itokawa here, and that's an image of Itokawa, the asteroid, and the orbit. But the characterization for the option B candidates, which is a completely different set, of course, is to get observational evidence that there are boulders on the surface of the asteroid. And I show on the right here an actual image of the surface of Itokawa. And some of those boulders are on the order of 2, 3, 6 feet, perhaps almost 10 feet in diameter, and those boulders would be appropriate for option B. So far, we have discovered and characterized, we have observational evidence for a few of boulders on the surface of a few asteroids. There are hundreds of possible asteroids to go to, but getting that last step, getting the evidence for boulders, is a difficult one. So let me go to the summary of what we have currently on the next slide here, the summary of current and future ARM candidates. So for option A, by our tally, we have 9 potential candidates. Those are the ones that looked good, roughly, and had roughly the right size. But in fact, 3 of those were found just last year. But the valid ones, we have 3 so far. The valid ones are those that we know the size accurately enough, and we know the mass, and they're within the capabilities of the asteroid retrieval vehicle to bring back. And those are named 2009 BD, 2013 EC, which is EC20, which is on a rather small one. And now, as of today, we're talking about 2011 MD, and you'll hear a little bit more about that from the next speakers. Additional valid candidates for option A are being added to this list at the rate of about 1 to 2 per year as we get more and more observational facilities. We're spending more time looking for these objects. We expect 1 to 2 per year. For option B, there are lots of potential candidates out there which are about the right size, but of those that have their surfaces characterized, we have 3. Itokawa, which was characterized by the Hayabusa 2 mission. We have 2008 EV5, which was characterized by radar. It came close enough that we could actually see evidence of boulders on the surface. And Bennu, which was characterized by radar in the past, and which will be characterized by the OSIRIS-REx mission in the year 2018. So they will be they are the current list of valid candidates for option B. And if we look at the rate at which asteroids of this size come close enough to the Earth that we can see boulders on the surface, that's about 1 per year. Okay, the next slide then is I'm going to move on to talk about one particular object, and that's 2011 MD, which will be talked about by the following speakers. And I wanted to just say a few words about the orbit of this object. You see the Earth and the asteroid 2011 MD in the lower right there. That is where they were located in the year in August of 2011, which was just a month or so after the discovery. The 2 orbits get really close together, just a little bit below that. The asteroid was discovered in June 2011 by the Linear telescope. You'll hear more about it in the later speakers, but what I wanted to say was that you see how close the asteroid is to the Earth. That is where Dave Tholen, who will be speaking shortly, observed it. The asteroid, being small, has to be very close to the Earth. If it's not, it's simply too faint to be observed. I wanted to say a few words about the orbit. Now, this particular asteroid is very close to the Earth in the year 2011, but if we now but it's on a larger track. You see the blue orbit is the orbit of the asteroid. We can ignore the red, which is Spitzer for now. The blue orbit is the orbit of the asteroid. It's on a farther track, and it actually takes a little longer, so the net effect is that it will fall behind the Earth. The next slide now, flash forward 2.5 years, and the Earth has moved over to that side of the Sun, and you'll see that the asteroid has fallen back about 1/4 of an orbit. And that's how far it has moved away from the Earth. It's certainly not visible from the Earth anymore, but it's near Spitzer, and that we took advantage of that opportunity to have it observed by Spitzer. I want to say one last thing, and that is that this falling back behind the Earth will continue with time, and the asteroid will eventually fall all the way back, and the Earth will lap it. And that happens in 2024, and that's the opportunity that we could use to capture the asteroid into orbit around the Earth. Thank you.
Thank you so much for that excellent summary, Paul. Now we'll go to the University of Hawaii, where Dave Tholen, who's an astronomer, will tell us a little bit more about 2011 MD and his colleague, Marco Michelli, who's joining us by phone. Dave and Marco, the floor is yours.
Hello.
Okay, good morning. As Paul Chodas just mentioned, the size of asteroid that NASA is interested in for a retrieval mission is fairly small, about 10 meters or smaller, about 30 feet or smaller. And that size of object is bright enough to be detected by the telescopes that we have here on Earth only when the asteroid is relatively close to the Earth. So if the asteroid is on an orbit that is rather dissimilar from the Earth's orbit, it will whiz past the Earth in just a few days. the number of observations that you can get, the length of time over which you can observe the asteroid is so short, you really can't establish the orbit very well. And in order to send a spacecraft to one of these small asteroids, you definitely need to know the orbit reasonably well. So what you need to have is the kind of asteroid orbit that is very similar to the Earth's orbit. And 2011 MD is one of those type of asteroids. When it came by in June 2011, we realized that it was on a fairly Earth-similar orbit, and as a result, we put in our observing plan several observations into the future to try and get that orbit pinned down somewhat better. In this particular case, we were able to track 2011 MD for an additional 73 days after discovery, whereas most of these small asteroids that are found by the sky surveys, just 3 or 4 days and they're gone, unable to observe, just too far away and too faint. But this one stayed close to the Earth for a reasonably long time. So the important point here is that the orbit of this asteroid is reasonably well established, and we can send a spacecraft to it. But in the course of doing these observations, we noticed that there was a very slight discrepancy between the position that we measured for the asteroid and the position that you might predict on the basis of the orbit determination. In other words, there was a slight departure from the motion you would expect just from the influence of gravity alone. And the reason for that is the sunlight falling on the surface imparts a very slight acceleration, very, very tiny acceleration. This tiny acceleration is really only detectable on small asteroids. As you get larger and larger asteroids, the gravitational force becomes dominant. As you go to smaller and smaller objects, eventually the effect of sunlight becomes the dominant force. And perhaps the best illustration of that is a comet tail. The actual nucleus of the comet is a much larger object, and it's much harder to move with the effect of sunlight. But the dust particles that get emitted as a comet outgasses can be very, very tiny, just small grains of rocky material, perhaps only a few microns in size. And those have such a small mass that gravity is almost negligible, whereas the sunlight that falls on them can push them around very easily. And that's why you see the tail of a comet usually stream in a direction away from the sun. So we're in a transition region here between objects that are very small, like the dust particles in a comet's tail, and larger asteroids. So the acceleration on the asteroid is very, very small, very difficult to detect. But on these really small ones, it is possible to measure that effect. And that is a very useful thing for physical characterization. And it's been done now for about 4 asteroids in this size range. And it actually became one of the key parts of the doctoral dissertation of Marco Micheli. So I'd like to turn the discussion over to him right now, and he can tell you a little bit more about the type of observations that we made to determine this acceleration by the force of sunlight falling on the asteroid, and some of the physical results that we got as a result of those observations. So, Marco, are you on the line?
Yes, I am. Thank you, Dave, for the introduction. Hope you can hear me. Well, Dave already introduced most of the technical part of what we did and why it was so interesting to observe this particular object, 2011 MD, and a couple other ones that we observed over the years. Well, they are small enough that we can actually see a departure of their motion from a typical orbit around the sun caused only by gravity because of this effect of the sunlight, which is actually pushing the asteroid slightly away from its orbit. So what we did was to observe this particular object, 2011 MD, for a long enough time that made this small displacement apparent in our observations. And why is that important? Well, as Dave said, if an object is light enough to be affected by this pressure of sunlight, well, we can measure how much it is affected and have an idea of how big and how light it is. And what we actually get is a measure of the cross-section of the object, so how, like, the area that's exposed to sunlight. And if we know something else, like if we know the size from other measurements, we can use this information to figure out the mass of the object. And as you may imagine, if the goal of NASA is to go and grab one of these asteroids and obviously transport it with a spacecraft, it's extremely important to know the mass of the object. So what we did was to get measurements of the position of this asteroid for a few months and use this together with an assumed value for its size to estimate the mass, and then when you have the mass, you can actually combine that again with the size and have an idea of the density of the asteroid. And two main things actually came out of this. Well, the first one, which is actually relevant for a possible space mission to an asteroid, is that the density was actually heavy enough to exclude that this object was artificial. Because, as you may imagine, if an object is in an orbit that is similar to the orbit of the Earth, it may be just an interesting asteroid, easy to reach, but there is also a chance that it is actually an artificial object. So we first wanted to exclude that it was artificial, and that is done by measuring the density and seeing that it's not light enough to be compatible with being a hollow metal cylinder or something that may look like a spacecraft or an upper stage of a rocket or something like that. The second thing we noticed, on the other hand, is that although the density is heavy enough to be compatible with being an asteroid, like a rocky object, it's actually much lighter than what we expected. It's not very easy to precisely constrain the density of an asteroid with this technique, but we can get, within a factor of 2, and our result was that it's actually very light. It's possibly lighter than water, so it has a density of less than 1 in the usual units, which is telling us a lot. It's telling us that this object is peculiar in the way it's made, and it probably has a lot of empty spaces inside the rock that makes it. So this is telling us that it's not a huge, big, heavy rock, but it's something more complex, which is another very important information for a possible future NASA missions to it. So, well, this was all based on our observations from the ground with the telescopes in Hawaii. The main thing that we couldn't directly get from that is the actual size that then we combine with the measure of this radiation effect to figure out the mass and then the density. So this is because it's really hard to get the size of an asteroid from the ground with only observations done with telescopes on Earth. It's actually much easier if you use a telescope like Spitzer that was mentioned before by Paul, and that's a perfect point to give to lead the speaker, the talk to the people at Northern Arizona, which will tell us how they use Spitzer to actually measure something more on this asteroid and help constraining how it's made. Okay, so I think the people at Northern Arizona can continue from here on. Thank you very much.
Dave and Marco, thank you very much for that presentation. So the mystery was deepening here on 2011 MD, and now we'll go to the team who used Spitzer to help answer some of those questions. We go to Northern Arizona University, where we're joined by David Trilling and Michael Momer. Gentlemen, the floor is yours. David, Michael,
thank you, Trent. I'm David Trilling here at Northern Arizona University. We're going to take a few minutes and tell you about our results that we've obtained on 2011 MD with the Spitzer Space Telescope. The first image that I want to show you is our final image that we obtained with the Spitzer Space Telescope of this asteroid 2011 MD. What you're looking at, this square image here, and the asteroid is the bright spot right in the middle of the image. There's several bright pixels together. This is a composite of about 20 hours of staring at the asteroid with the Spitzer Space Telescope. That was earlier this year, as Paul showed, in February of 2014. We stared at the asteroid for 20 hours, and the image you're looking at is actually a stack of about more than 600 individual images all stacked together to make this final composite image where we can measure the brightness of the asteroid. Now, why do we use the Spitzer Space Telescope at all? That's shown on the next figure, which is a two-panel figure. It has visible light on the left side and infrared light on the right side. As Marco mentioned, when you look at an asteroid only in visible light, the light that most telescopes work in and that you can see with your eyes, you cannot directly measure the diameter of the asteroid. And that's indicated on the visible light side of this panel, these three circles at the top. You could imagine an asteroid could be small and highly reflective, that's the left circle. It could be large and have a low reflectivity, that's the right circle. It could be an intermediate case. And all three of those would give you the same apparent brightness in visible light. So you can't tell the diameter of the asteroid using visible light only. However, if we go to the right side of this, in this figure, the right panel, where we observe an infrared light, as we do with the Spitzer Space Telescope, in infrared light, the measurement of the brightness of the asteroid tells you directly the diameter of the asteroid. So we use Spitzer, we measure the brightness of the asteroid, that immediately tells us the diameter of the asteroid, which then allows us to derive additional physical properties of this asteroid. Now, one thing I want to mention is that the Spitzer Space Telescope is the only facility that can make this kind of measurement that we're talking about here.
So my name is Michael Mommert. I'm a postdoc here at NEU. And so from our Spitzer observations, we derived the infrared brightness of this object, and we combined it with a measurement of the brightness in the visible light. And we put both those numbers into a computational model which gives us the size and the surface reflectivity of this object. We did this as part of our analysis, which has been published as of today in the Astrophysical Journal Letters. And the main result of this analysis is that the diameter of the object, so the diameter, or most likely diameter of 2011 MD is 6 meters, which is about 20 feet or the size of a delivery truck. So you might actually be able to put this asteroid into your garage at home. As a second step in our analysis, we combined our diameter measurement with the precise positional measurements of our colleagues in Hawaii, Dave Thole and Marco Micheli. And we found a density which is which is a little higher than their density estimate, but it is consistent with their result. And the density we find is about 1/3 the density of solid rock, which is about the density of water. So this object might actually swim if you put it in a swimming pool. We derived the mass of this object as 100 tons, which is just a function of the diameter and the density. And the fact that the density we find is lower than the density of solid rock tells us something about the internal structure. So on the next slide, there is an illustration of the porosity. Porosity means, or porosity is a measure of how much empty space there is in an object. So there are 3 different objects on this slide. On the left-hand side, there is a solid rock depicted, which has a very low which has a very low density or porosity. Sorry, it has a very low porosity because it's just a solid piece of rock. If you would shatter this object, and you would drive apart the individual particles from that, you would increase the amount of empty space between the particles, and you would increase the porosity. So in the case of 2011 MD, we found a porosity of about 65%, which tells us that about 2/3 of the object, or the volume of the object, is empty space, and only 1/3 is rock. So this is, as Marco already said, this is pretty unexpected because traditionally people thought that small asteroids like 2011 MD are just single pieces of rock or single boulders floating in space. So our last slide shows an artist's conception of what 2011 MD might look like. So on the left-hand side, there is a structure which we refer to as a rubble pile structure, which shows the asteroid as basically a cloud of objects, a cloud of boulders that are confined to a limited space, float around in space together, and they are bound by their gravitational forces or other forces. On the right-hand side, there is a different concept which shows the asteroid as a solid piece of rock, as a nucleus that is surrounded by a cloud of dust and pebbles. So those are just two possible possibilities what the object might look like. There might be other ones. And so what we would need to really find out what it really looks like, we would need more observations, either from telescope observations or from space mission data. But as Paul already said, this won't happen in the next decade. So yeah, we will have to wait for a decade to find out what it really looks like. And yeah, that's it. I give back to Trent.
Great, David, Michael, thank you so much. So now we'll come back here to Washington before going to Ames to hear from Jason Kessler, talk about the Asteroid Grand Challenge, and we'll soon take Q&A from media. And just a reminder to those of you watching online, you can, of course, ask your questions on Twitter using the hashtag AskNASA. But first, I'd like to come back here to headquarters to hear from Lindley Johnson and Michelle Gates for any of their analysis on the implications of what we just heard for NASA's either detection of asteroids or specifically the Asteroid Redirect Mission.
Well, let me take it, Trent. Over the last several minutes, you've heard the process that we go through once we find an object to determine what its size, what its composition, what it is that we might actually be looking at if we were to go with a spacecraft. Everything we can do short of actually sending a spacecraft to it. So you see, it's a process that one observation leverages off another observation to build up this story or understanding of what kind of object we may be looking at. This is what we have as far as information on this particular object, 2011 MD. It looks to be within the range of characteristics that could be captured by our option A. But we will continue to look for objects through our program, and when we find ones that are in the right orbit, we'll do this characterization project to understand as much as we can about the object and add it to our pool of potential candidates for the mission.
So as Emily said, there's much more observation to come, and of course there are ways for the public to participate in that hunt for asteroids. And next we'll go to Jason Kessler at the Ames Research Center, Moffett Field, California, to tell us a little bit more about NASA's Asteroid Grand Challenge. Jason?
Thank you so much, Trent. It's great to be with you here from Ames, and a big thanks to the members that have spoken before me. It's always such a thrill for me to be able to hear the progress that's being made in the Asteroid Redirect Mission, and a real big thanks and congratulations to Michelle and Lindley for the incredible job they're doing in managing the efforts so far. So if we can transition now into the Asteroid Grand Challenge, if we could get the first slide. We announced on June 18, 2013, the Asteroid Grand Challenge to find all asteroid threats to human populations and know what to do about them. And I think as we clearly heard just now, there is a strong group, an international group that's working on the asteroid problem. And the reason we announced this grand challenge was not because there was an impending threat or because we didn't feel like we were doing the job. It was a recognition that NASA has used open innovation tools in the past very successfully. And we thought, might be an interesting way to engage the public to see if we could accelerate some of the great work that's already being done. And it is a testament to the folks on the front lines that are doing this work. It is not easy work. And so if we go to the next slide, we'll see that the first year has really been around creating awareness, because this work is not easy. And when we think about engaging the public, we wanted to begin the conversation and let people know what the issues were and start to feel out what communities might be interested and appropriate for us to engage with. One of the more exciting things we've done in the last year, Trent mentioned the Solar System Exploration Research Virtual Institute, or SERVI, which is based here at Ames. SERVI put together a number of workshops. We had, in fact, a couple of the panelists, Lindley and Paul, were a part of speaking through the Asteroid Grand Challenge seminar series. And we had 40 minutes from asteroid experts sharing their perspective and their work, and then opened it up to 20 minutes of questions from the public, and recorded all that. So we were building a library of information that will be continually available and accessible to the public online, so they can figure out, are there areas that they want to plug into. Moving to the next slide, another area that we got excited about was tying into the already very successful International Space Apps Challenge. Nearly 100 cities across the globe participated in a weekend-long hackathon, if you will, and asteroids was one of the themes. And we had about 5 projects that people could work on, and surprisingly, we got 163 projects developed by this community that got forwarded into global judging. So these were projects that were deemed worthy by the local communities there as being reviewable by a larger audience. Unfortunately, the competition was quite steep, and none of those projects did move on to finalists. But I think it's a testament to the interest of the public around asteroids that we saw so many projects voted up. Moving on to the next slide, you'll see on the right there, Space Gambit. We have a Space Act agreement with Space Gambit, and they are engaged in helping the maker community open up the frontiers of space. And one of the really exciting things that has happened with Space Gambit, we had reached out with them to try and figure out how to build some educational materials. They've in fact now received 28 proposals, all asteroid related, and they've down selected to fund 11 of those that will be worked on this summer and reported out on in September. 2 of those winners came from the Space App, so we're starting to see that connection from activities NASA's already doing, tying it into the asteroid work, and seeing ways to take it a little bit further. In the middle of that slide, if we can go back, you'll see SLU. SLU is a really interesting membership model. It enables citizens that don't have a backyard or don't want to invest lots of dollars in a telescope to get access to professional class observatories, primarily in the Canary Islands. We've engaged with SLU to try to increase the number of amateurs that are contributing to characterization work, and expect some curriculum development to follow along with that as well. And then finally, you'll see planetary resources. We announced the Space Act agreement with them back at the Idea Synthesis RFI workshop in the fall. The goal in that Space Act agreement was to develop an algorithm initially that was as good as the current algorithms in determining false positives. We have closed that first round of competition. It ran through the NASA Tournament Lab and on Topcoder, and $10,000 in award money has been made available to the top 5 winners of that challenge. And the second phase, which is moving into developing a brand new algorithm to search through existing data sets to find asteroids that might have been missed, that challenge will go live in July. In addition to that Asteroid Data Hunter Challenge with Planetary Resources, we also have currently a live Asteroid Tracker Challenge running on Topcoder as well. And that's an effort to try and figure out how best to place radar dishes to help when NEOs are flying nearby Earth. So that algorithm challenge will go live in July as well. So you can see there are already a handful of ways for people to be participating and actually win money as they help us with our work. If we go to the next slide. So now we're moving into year 2. We've already had lots of conversations. We've attended 2 maker fairs. We've spoken to numerous communities, had online forums, and we're really interested in taking a lot of the better ideas that we got from this past year and figuring out how to move forward with the community to co-create an implementation plan. And so that will really kick off as we wind down this session at 3 p.m. Eastern. We're going to start the Asteroid Grand Challenge Anniversary Seminar Series. We have an Asteroid Data Hunter session. It'll be a 90-minute session with professional and amateur astronomers coming together to think about how can we do characterization work with amateurs to help with the follow-up. It was mentioned a number of times earlier today just how critical the characterization is, and we want to figure out a really solid plan to engage amateurs to help with the new discoveries. As Paul mentioned, the rate is increasing over time of new discoveries. After that session, we'll move into a Minor Planet Center and a data usage session. We've recognized that there is a fair amount of data out there that maybe not in the easiest format for people to work with. We've seen lots of great visualizations that have helped people understand what the situation is and imagine a different future. And so we're going to talk with coders and designers and my good friend Jose Luis Galache from the Minor Planet Center to think about how might we utilize those data sets in ways that are useful in communicating to folks. That'll wrap up today's activities, and we'll move into a session tomorrow morning. David Morrison, the Survey senior scientist, will be giving approximately a 40-minute talk about the near-Earth objects problem and why this is a grand challenge. And that will then be opened up to questions for the public to ask and get a deeper understanding of what's going on. From there, we'll transition into another 90-minute session. This will be with the makers. I mentioned Maker Faire, I mentioned Space Gambit. We recognize the energy and ingenuity of this community as a really great opportunity for us to figure out how can we partner with makers to come up with solutions that we haven't yet thought about. And so we'll have a number of luminaries in the maker community talking about issues that they have and trying to map out some reasonable plans that would deliver something tangible that would help solve this grand challenge. And then finally, we'll close out the seminar series with a next generation engagement session. We're going to have communicators, educators coming together to try to think through what would we need to do over the next coming years to really communicate to folks and enroll them and their assistants in, even if it's not sitting behind a telescope or building an algorithm, but communicating to their communities and bringing people together on this potentially very real threat. We can move to the final slide. There you can see the URL for the seminar series. I hope you'll stick around and join us. We expect to have really lively conversation that'll be open through the Adobe Connect chat window for people to ask questions, as well as on the hashtag AsteroidGC. And it really is an opportunity for all of us to prove that we are smarter than the dinosaurs and see what we can do to help this expert community that is already doing a really outstanding job looking out for us. With that, I will turn it back to Trent, and I thank you very much.
Thanks very much, Jason. And just to help punctuate that, there's some really incredible opportunities for the public to get engaged in the search for asteroids. Jason just recounted them. So again, more information at www.nasa.gov/asteroid initiative. Very exciting two-day workshop about to start after this event and continue on to tomorrow if you'd like to find out the ways that you can help participate in the search for asteroids. So with that, we'll circle back and we will begin a Q&A. I think we have some reporter questions here in the room on the line, and then we'll go to your questions on Twitter. And again, you can ask questions of our panelists using the hashtag AskNASA, and we'll start here in Washington with Space News' Dan Leone.
Hi everybody, Dan Leone with Space News. Please excuse my voice. So my questions are for Lindley and Michelle here in the studio. The latest candidate asteroids, when would those be retrievable to the desired lunar parking orbit? And when will you select one of the two mission concepts? And then, as a parenthetical, what's the most important selection criteria in there? Is it going to be the cost of the mission, the relative ease of the mission, the extensibility of the retrieval craft to other future missions, etc.? Thank you.
Want to take part one?
Well, as far as when these candidates would be accessible for the redirect mission, it depends on what orbit they are in and their position relative to the Earth when they come back to the vicinity of the Earth. But all of the candidates that we've talked about, we've determined that their orbits are such that they are in that positions, sometime in the early 20s. By candidate, it varies from 2021 to 2024. 2011 MD, which we specifically talked about, its opportunity to redirect it into the lunar orbit is in 2024. But it does, it depends on the orbit, the size of the object, and what option is used, quite frankly, as to when the robotic spacecraft has to arrive at the asteroid and begin the redirection, and then how long it takes to move it into the lunar orbit. But all the candidates we talk about, they are viable candidates because they fit within that window of the early 20s, 2021 to 2024.
Yeah, so all the candidates on our target list fit in that on our valid target and candidate target list fall in that time frame. The schedule for down selection of the robotic mission concept is currently for that decision point to take place late this year, likely mid-December, and would feed into our mission concept review in February of next year. We don't plan to, nor do we want to, stop actually looking for targets at that time. Our current schedule shows that we wouldn't need to actually make a final selection of a target until 1 year before launch. And we'd like to actually keep looking and allow our esteemed colleagues and the assets that they're bringing online to continue to find potentially better and better targets. So the criteria of which the final selection would take place is still under development, and we actually plan to share that thinking throughout the year with the community and look forward to hearing any feedback.
Thank you. Okay, so we'll go to the phone lines now, and for the reporters there, if you wouldn't mind trying to direct your question to any of the specific speakers that you've heard from today, that'll help us with the video and the audio sources. But we'll begin on the phone line with Seth Bornstein of the Associated Press. Go ahead, Seth.
Yes, thanks for doing this. This is for Michelle and Lindley there in D.C. First, the option B is not one that was originally talked about. Is it more of a secondary option than the first? Because, I mean, you're not actually redirecting an entire asteroid. Why even bring up the whole concept of option B? Is it a safety, a money issue? And then my second question, and please answer this. Don't avoid that since it's a two-part question. Have you got a cost estimate either for A and the cost estimate for B, or just a cost estimate? How much is this going to cost taxpayers? And finally, if it's this rubble pile, how do astronauts not get hurt with all the schmutz hanging around? Thank you.
Sure. So I might need a little help actually with reminding me what one was. Oh, I remember. So you might remember from last year that the what we called the reference concept for the redirect mission was the enveloping of a single free-floating small asteroid. As part of our trade studies and analysis of alternatives that we did over the summer, we looked at several other both system and mission concepts. And what we're now calling option B and option A, as a result of the programmatic and technical risk assessment that we did over the fall and presented much of it at the Opportunities Forum, are equally weighed at this time. We're going through additional technical risk understanding and risk reduction for both capture options, as well as the continued search and characterization of the potential candidates to come to that down select decision late this year that I talked about earlier. On the cost, of course, our internal studies have resulted in increasingly refined cost estimates for both options. And we do consider them both to be equally on the table and both within the overall cost envelope that the Associate Administrator actually mentioned in one of the forums, the Strategy Forum or the Opportunities Forum in spring of this year. I think it was the one in April, which was approximately half the estimated value, the estimated cost of the Keck study concept. And then what was the
So it was 1.25 billion roughly, right? If the original concept study was 2.5 billion, and half would be about 1.25.
And so we still fully expect, I mean, as Robert Lightfoot said, that that development estimate would come within that range.
Or less, right?
So can you?
And Seth, sorry,
what was number 3?
The third question was about the rubble pile and its safety for the crew.
Take the rubble pile question.
Okay, well, what you saw depicted by the folks at Northern Arizona University is some of their idea of what the object might look like. Just a couple of examples. I would kind of describe those as maybe kind of extreme examples. It all depends on what the specific composition of the material is. They gave some depictions of if it were solid rock. You see this bunch of rocks, rather large rocks flying together. If they're more of a porous rock, then it would be a tighter coupling. But this rubble pile structure, which you see, by the way, on the slide that's up at Itokawa, that's a larger asteroid that is what we consider a rubble pile, and the density of that object is not solid rock either, because it is a conglomeration of smaller rocks and pebbles and dust that is just held together by their mutual gravity. So the depiction images that you saw, I think, are maybe on the extreme side of what might be encountered. I would expect it to be a more closely consolidated object that, for the option A, could be encapsulated in this inflatable structure, inflatable bag, if you want to call it that, and all contained within that bag.
Let's go back to the phone line, and we will go to Alan Boyle, MSNBC. Go ahead, Alan.
Yes, hi. I think this is probably for Lindley. I think a lot of people are, when they hear asteroids, they are thinking Armageddon or Deep Impact, and want to hear what these initiatives have to do in terms of addressing the potential threat from asteroids. Maybe you could provide a little more information on this subject, and perhaps there are ways that the asteroid retrieval mission could pursue those goals. I know that you mentioned one of the targets is asteroid Bennu, which is considered a potentially hazardous asteroid. So, is that the sort of thing that you want to address in the mission ahead and in the initiatives that you're following for learning more about asteroids? Thank you.
Question.
Sure. If you're doing the movies, do a wonderful job of planting in people's heads an image of what we're talking about. Unfortunately, it's not always what you see in Hollywood is not always reality. But these what we're doing here for the ARM mission is what we consider sort of a subset of what we're trying to accomplish with the Near-Earth Object Observation mission. Because we are trying to find the population of asteroids that could potentially be a hazard of impacting the Earth someday in the future, we're naturally looking for all the objects that come into close to the Earth and have Earth-like orbits. They're a subset of that overall population. So in doing our larger mission of finding the NEO population, we are finding a subset of potential targets. Now, in talking about, so what does the ARM mission do the other direction for the planetary defense mission? The capabilities that we're looking at for demonstration by the robotic spacecraft are adding to our knowledge and techniques of what might be done for an asteroid that's on a hazardous trajectory. And in fact, that's one of the reasons why we started looking at option B, because with option A, the size of the asteroid is very small, less than 10 meters in size. That would never represent a hazard to the Earth because that's such a small size that the Earth's atmosphere does a very good job of protecting us from any object that small. They burn up, they come in and you see them as meteors and they burn up, and maybe there would be some meteorites that would survive the entry, but there's really no great hazard. We see those kind of events in Earth's atmosphere at least several times a year. But for testing of planetary defense techniques, redirection or deflection of an asteroid that is a true hazard, that we would want to prevent it from impacting the Earth. That's what led us to looking at maybe we could do something on this mission with a larger asteroid, and before we pick up a large boulder from this larger asteroid, do some demonstration of deflection techniques. One that is certainly on the table and looks very attractive is a demonstration of a gravity tractor, which is by the gravity mutual attraction between the spacecraft and the asteroid, gravitational attraction. You can slowly tug the asteroid off that hazardous trajectory. Now we could do that demonstration before we pick up the boulder, or even better, we can do it after we pick up the boulder and do what we are calling an enhanced gravity tractor demonstration, where we are using that mass of the boulder to enhance the mass of the spacecraft, and we have an even more a greater gravity attraction between those two objects, and therefore you can affect the trajectory difference in a shorter period of time. So that's how these two things are kind of related, and we're supporting the ARM mission with our observation program, and in turn the ARM mission can support our planetary defense objectives by doing some demonstration of the techniques and technology that would be used to deflect a hazardous asteroid.
Just add, that's a great additional distinction between option A and option B, and was in fact one of the driving interests for pursuing the detailed study of option B that we did last year.
Okay, thank you, Alan. Let's take a few questions from social media. We'll start here. Jason.
Wonderful. This question comes from Twitter user Jason, who asks, the artist's conception of 2011 MD was a rubble pile. Would you snag the entire pile using ARM option A?
Just again, emphasizing on a couple points Lindley just made, the option A inflatable structure is actually designed to envelop a variety of mechanical different configurations of the candidate asteroid. And so ideally, we'd be able to capture all of the large portions if indeed one of those artist's conceptions is accurate. And, you know, the dust components and those would probably, we think, potentially be, remind me again of, actually, Paul had the answer. I don't know if we can go back and forth, but Paul mentioned last week.
Well, it wouldn't be dust that would be around the object, because as we were talking earlier in the interviews, that solar pressure will quickly blow the dust away from an object. So it's more likely
pebble-like structure.
A small pebble-like structure that's around it. But you need to keep in mind that this is all material that is orbiting together, so it has the same relative velocity. And with the capture spacecraft, we are matching the velocity to move up on it and capture that material. So it's not like this material is moving at even feet per second different velocity. So its ability to really do any damage is negligible. But with the option A concept, it is to envelop the entire material, and our estimates on the size and mass of that material shows that it's within the bounds of what the option A can achieve. So yes, we do intend to encapsulate the entire object.
Let's take another.
Wonderful. This question comes from Twitter user JP, who asks, how will the arm help to deflect potentially hazardous near-Earth objects?
So yeah, could you maybe recap a little bit?
Right. Yeah, I went into that in the previous answer, but we do intend to demonstrate a couple of different techniques. One would be what was called the gravity tractor, with the relative gravitational tug between the spacecraft and the asteroid, either before or after it has the mass. But also another technique that is being talked about is what is called an ion beam deflection, where we use the ion thrusters that are on this solar electric propulsion spacecraft, and we use it and turn around and actually blow against the asteroid, and the ions impacting on the asteroid surface is like sunlight. Gives it a momentum transfer, and will slowly move it off of its natural trajectory. And that technique could be demonstrated either with option A or option B. So there are several things that are being looked at here that offer a demonstration of planetary defense techniques.
Let's go back to the phone line, and we'll begin with Alexandra Witsy, I think it is, with Nature. Go ahead, Alexandra.
Yes, great. Thanks for your time. I wanted to ask about the future of Spitzer. It came out sort of on the cutting block in the recent Astrophysics Senior Review. What are the implications for follow-up studies of some of these objects if Spitzer is no longer operational? I guess this is for Lindley Johnson. Sorry.
Our take that. Well, with the Senior Review, the Astrophysics Division's Senior Review, they would certainly like to keep operations going on all of their available spacecraft, but with the budgeting, the missions are budgeted for a certain period of time, of which Spitzer fiscal year 2014 is where that budget ended. But the Spitzer spacecraft is still a viable spacecraft, and we're in the lucky situation where the spacecraft continues to have a good life, and could continue operations. And we'd certainly like to be in that situation versus the other situation where the spacecraft dies before we want it to. But because it's not in the future budget plan, we have to look at alternatives, other ways that we could continue to fund the operations of Spitzer, and that is what is being done. We are the Astrophysics Division within the Science Mission Directorate is looking at other opportunities as to how the operations could be funded. I know the next question is probably going to be, so how much a year does it cost to operate Spitzer? The budget in 2014 for Spitzer was $17 million. Now that you could see in planning of operations of maybe we don't operate it full time, maybe we only operate it part time, so the cost could be reduced. We could bring in other institutions and sources of funding. So all those options are being looked at for continued operations of Spitzer.
Okay, we'll take our next question with Irene Klotz, Reuters. Go ahead, Irene.
Thanks very much. Two questions. The first is the total amount of money that NASA expects to spend on those concept studies. I think when the BAA was announced, it was up to $6 million for up to 25. So if that number is still valid. And then I wasn't really understanding if this 2011 MD is actually like the leading candidate now, or are you all just kind of emphasizing it because you have these new results from Spitzer? Thanks.
Good question. I'll take the cost one. So yes, originally in the announcement of the BAA, NASA had allocated up to $6 million to fund, the thought was up to 25 proposals. There was a two-step review process, which actually Dr. Chris Moore in the Human Exploration and Operation Mission Directorate deserves a huge amount of credit for the comprehensive, high quality, and very quick review process that he led, and all the teams for their work. And so as a result of the looking at evaluation against the criteria through both the first step, which is the peer review process, and then the second step, which was the programmatic review process. There were 18 proposals that were ultimately selected at a total of $4.9 million. You want to take the?
Sure. Well, in talking about 2011 MD and where does it fall in our list of candidates, people keep asking us, what's the target for the mission? What's the target for the mission? Well, what we want to have is a lot of potential candidate targets for the mission when it comes time to make that decision. We don't want to be restricted to just one, because the risk of that one object being exactly right for the mission and all the risk being minimal is for one object is probably not good. So if you have a list of various candidates you could go to, plus if you run into a launch slip or something, that could eliminate the one target that you were looking at. So if you have a list of these candidates, that's certainly advantageous. And we are working to have a fairly large list. It won't be dozens, but it may be 10 or so by the time we get to the time to make the decision. So we're having a nice list of candidates to select from. People were asking us about that. The occasion of the results from the Spitzer observations of 2011 MD provided us the opportunity to talk to you about the process by which we are selecting candidates and looking at them, of which 2011 MD now is one of those candidates.
Thanks, Irene. Let's go back to one or two more social questions before we wrap up. Go ahead, Jason.
Sure. So there's a couple of questions here that have come in from different Twitter users. Joselita asks, what are you planning to redirect the asteroid to? And then in the same vein, Charlotte asks, how big is this that you're planning on redirecting?
So I'll take the first part again. We're planning to redirect the asteroid to a stable orbit in the Earth-Moon vicinity, and it's actually a family of orbits called distant retrograde orbits. The particular one that we have in mind is about 75,000 kilometers above the surface of the Moon, where both the asteroid and the high-powered solar electric propulsion-driven spacecraft would be anticipated to be stable for over 100 years. So it is a very stable orbit. You want to take the second part?
And the size was?
Yeah, the size.
Well, sure. I mean, the size is, I mean, the real factor that has to be looked at as far as redirecting the asteroid is, you know, what mass can the spacecraft handle, redirect to this lunar orbit. But looking at the sizes that could be done for one whole asteroid, it has to be something that's less than about 10 meters in size. The particular object that we talked about today, our best estimate of its size is about 6 meters in size. If we were to get a large boulder off of a larger asteroid, it's going to be something in the 2 to 4 or 5 meters in size. It all depends on what orbit the asteroid is in initially, its natural orbit, to determine how much mass could then be brought into the distant lunar retrograde orbit, but less than 10 meters in size.
Well, I want to thank everyone for their participation today. We had a lot of participants with us virtually and here in Washington, and I just thank you all, to all the speakers. We covered a lot of news today. Certainly we talked about broad agency announcement, awards to contracts to come, some of the proposals that were accepted to advance the Asteroid Redirect Mission. We've talked about our observation of asteroids. We've talked about the Asteroid Grand Challenge, that are ways that the public can help in the participation, help participate in the search for asteroids. And we talked about Asteroid 2011 MD and Spitzer's observations of it, and why that's a target, an interesting, valid candidate, I should say, for one of the options being considered for the Asteroid Redirect Mission. All of that will be recapped on nasa.gov/asteroid initiative. We'll have content that goes through the who, what, when, where, why, and some of the basics on that for you if you look at the website a little bit later today. For now, I just want to thank everyone again for their participation. Thank you for joining, and especially thanks to everyone behind the scenes who helped us make all of that work. So thanks again from Washington, NASA headquarters. I'm Trent Parado. Thanks.